Good morning, everyone. I'm delighted to welcome you to today's presentation. Today, we will be exploring the fascinating topic of paging in operating systems. My name is Subhasree Maity, and I am an assistant professor in the Department of Computer Science and Engineering at Swami Vivekananda Institute of Science and Technology. Over the course of this presentation, we will cover the fundamental concepts of paging, how it works within operating systems, and its significance in managing memory efficiently. So, let's dive in and explore this important aspect of computer technology together. Let's start with an introduction to paging. Paging is a memory management technique that effectively eliminates external fragmentation, which is a common issue in other methods. It allows a process's physical address space to be non-contiguous, giving us more flexibility in how memory is allocated. In this approach, memory is divided into fixed-size blocks called frames. Think of frames as the building blocks of physical memory. On the other hand, logical memory, the address space that the process perceives, is divided into blocks of the same size, known as pages. This similarity in size between pages and frames is crucial because it makes the process of translating addresses much more efficient. Overall, paging helps us manage memory more effectively by allowing non-contiguous allocation, reducing fragmentation, and simplifying address translation. This concept forms a foundation for understanding how modern operating systems handle memory management smoothly and efficiently. Let's explore the basic concept of paging. In this approach, the logical address space, which is what your programs see, is divided into smaller, manageable units called pages. Now, on the other side, the physical memory, which is the actual RAM, is divided into frames. Each page from the logical space is mapped to a specific frame in physical memory. This mapping is crucial because it allows the system to efficiently manage memory and run programs smoothly. The operating system plays a key role here. It maintains a page table that keeps track of which pages correspond to which frames. This table is essential for translating logical addresses to physical addresses during program execution. Understanding this concept is fundamental because it underpins how modern operating systems handle memory management efficiently. Let's take a closer look at the structure of the paging system. When the CPU generates a logical address, this address is actually divided into two parts. The first part is the page number, often represented as P, which acts as an index into the page table. This tells us which page we're referring to within the memory. The second part is the page offset, or D, which specifies the exact location within that page. Now, to find the actual physical address in memory, we combine the frame number, which we retrieve from the page table based on the page number, with the offset within that frame. So, essentially, the physical address is made up of the frame number plus the offset. This structure is fundamental because it allows us to efficiently translate logical addresses into physical addresses, enabling the memory management system to handle large address spaces with flexibility and security. It's a core concept that underpins how paging works in modern operating systems. Let's take a closer look at address translation in paging. When a program accesses memory, it uses a logical address, which is composed of a page number and an offset within that page. The operating system then steps in and uses the page table to find the actual frame in physical memory that corresponds to that page. Once it has the frame number, it combines it with the offset to form the physical address. This physical address points directly to the location in RAM where the data is stored. All of this translation process is handled seamlessly by the Memory Management Unit, or MMU, which makes the whole system efficient and transparent to the user. This process is fundamental to how paging allows us to use memory efficiently and securely. Let's take a closer look at the page table. Essentially, it's a data structure that helps us keep track of how pages in virtual memory are mapped to frames in physical memory. Think of it as a directory that tells us where each page is located in the main memory. Each entry in the page table contains some key information. First, there's the frame number, which indicates the specific physical frame where the page is stored. Then, we have control bits. These are flags that provide important status information about each page. For example, whether the page is valid or invalid, which helps the system know if the page is actually in memory or not. Other control bits include protection bits, which restrict access for security or stability reasons, a modified bit that indicates if the page has been changed, and a reference bit that tracks if the page has been accessed recently. It's also important to remember that the page table itself is maintained in main memory, which means the system can quickly access and update it as needed. This structure is fundamental to efficient memory management, ensuring smooth translation from virtual addresses to physical addresses during program execution. Let's take a closer look at the hardware support for paging. First, we have the Memory Management Unit, or MMU. Its main role is to perform address translation, converting virtual addresses into physical addresses so that the system can access memory efficiently. The MMU is essential for enabling virtual memory management, which is a cornerstone of modern operating systems. Next, we have the Translation Look-Aside Buffer, or TLB. Think of the TLB as a small, super-fast cache that stores recent page table entries. Because these entries are accessed frequently, having them readily available in the TLB drastically reduces the time spent translating addresses. This means that when a process requests memory, the address translation happens quickly, improving overall system performance. By storing recent mappings, the TLB effectively minimizes the latency involved in address translation. This synergy between the MMU and TLB is critical for making paging efficient and ensuring that memory access remains fast and responsive. So, in summary, the hardware support, comprising the MMU and TLB, not only makes address translation possible, but also optimizes it to keep our systems running smoothly and efficiently. Now, let's talk about some key advantages of paging. First, paging eliminates external fragmentation, which is a big deal because it allows the system to make better use of memory by avoiding wasted space between allocated blocks. This means we can allocate memory more efficiently without gaps. Second, it simplifies memory allocation overall. Instead of dealing with complex memory management, paging breaks memory into fixed-size pages, making allocations straightforward and predictable. Third, paging allows for efficient use of physical memory. Since pages can be loaded and swapped independently, the system can optimize how memory is utilized, reducing waste and improving performance. Lastly, one of the most powerful benefits is that paging supports virtual memory systems. This enables us to use more memory than physically available by swapping pages in and out, which is essential for running larger applications smoothly. So, in essence, paging helps us manage memory more effectively, making our systems more flexible and capable. Now, let's take a look at some of the disadvantages of paging. First, there's the issue of internal fragmentation. Because pages are of fixed size, sometimes memory isn't used as efficiently as we'd like, leading to wasted space within pages. Next, we have the overhead of maintaining page tables, which can become quite significant as the system scales up. This means additional management effort and memory usage. Additionally, paging requires specific hardware components like the Memory Management Unit, or MMU, and Translation Look-Aside Buffers, or TLBs. These are essential for translating virtual addresses to physical addresses quickly, but they add complexity and cost to the system. Lastly, while page tables are incredibly useful, looking up addresses in them can slow down performance if these lookups aren't optimized properly. So, while paging offers many benefits, understanding these limitations helps us make better choices for system design. Let's take a closer look at the different types of paging. First, we have simple paging, which is quite straightforward. It involves basic page-to-frame mapping, where each virtual page directly corresponds to a physical frame. This method is simple, but can become inefficient as the system grows. Next, there's hierarchical paging, which introduces multi-level page tables. This approach helps reduce memory overhead because instead of storing one large table, we break it down into smaller, manageable levels. It's especially useful in systems with large address spaces, making the paging process more efficient. Then we have hashed page tables, which are particularly suited for very large address spaces. By using hash functions, these tables allow faster access to pages because they can locate page entries quickly, even in massive memory environments. Finally, inverted page tables take a different approach altogether. Instead of having a table per process, there's a single global table for the entire system. It's indexed by frame number, which makes it more memory efficient, especially when managing large systems with many processes. Understanding these different types helps us see how paging strategies are tailored to meet the needs of various system architectures and performance requirements, which ties into our overall goal of efficient memory management. Let's walk through an example of address translation to see how it works in practice. Suppose we have a page size of 1 KB, which is 1024 bytes. Now, if we look at a logical address of 2049, we can break that down into a page number and an offset. The page number is 2, and the offset within that page is 1. Next, we consult the page table to find the frame number corresponding to page 2, which is frame 5. To get the physical address, we multiply the frame number by the page size, so 5 times 1024, giving us 5120. Then, we add the offset, which is 1, resulting in a physical address of 5121. So, what does this tell us? Essentially, the logical address 2049 maps to the physical address 5121 through this translation process. This example highlights the core concept of how virtual memory management works. By translating logical addresses into physical addresses using page tables, allowing us to efficiently manage memory and ensure proper access control. Now, let's wrap up with a quick summary of what we've covered. Paging is a technique where memory is divided into fixed-size pages and frames, which helps in organizing memory more efficiently. This approach not only makes memory allocation easier, but also enhances protection, ensuring that processes don't interfere with each other. One of the key benefits of paging is that it eliminates external fragmentation, which used to be a big issue with contiguous memory allocation. However, it does introduce internal fragmentation, meaning that sometimes there's wasted space within the pages. Finally, it's an essential part of implementing virtual memory, allowing systems to handle larger processes more flexibly. Understanding paging is fundamental to grasping how modern operating systems efficiently manage memory.